Hello everyone. We're going to jump ahead in topics a bit today. I want to make sure you're prepared with some knowledge of assembly language as we are starting labs, and therefore we're going to jump ahead to what's covered in Chapter 7 of the text or course notes, which is assembly language programming. Okay, or in other words, telling the computer what to do. Okay, so this is clearly an essential part of the course, and understanding the organization of a computer is how do we give it pass instructions to the computer to tell it what exactly it is that we want the computer to perform in terms of an operation. Okay, so operations inside the computer are processed within the CPU or central processing unit. Okay, and within the CPU we find a number of critical elements to the execution of these various operations. Okay, one item that you'll see that we make extensive use of with our instructions and as we write code is the number of storage registers. So storage register is just a small bit of memory that's temporary memory, volatile memory, that is there to temporarily store data as we are manipulating data in instructions, and as we're passing data into instructions we will use these registers. Okay, there is generally a small number of registers within a CPU, and specifically in the NIOS-2 there are 32. Now, some of those registers are special purpose, and we'll look at that in a little bit more detail here in a second. Each register will have some n number of bits. This is generally a function of the width of the data bus. Sorry, a little glitch in my system there. The number of bits that are bits wide each register is generally a function of the width of the data bus, but specifically in the NIOS-2 processor they are 32 bits wide. Okay, if we pull up the introduction reference document for the NIOS-2 processor, so you can find this on D12 under Lab Reference Material, Introduction to NIOS-2 Processor. And if we scroll down a bit, so this gives many details on the processor. I encourage you to have a look at it heading into the labs. One of the, on the specific topic of registers, if we look on page 4, you'll find the various registers listed. Okay, you'll note that a few special purpose registers in the 32 registers that are available. Register 0, you'll note that in our examples of the labs, we've used register 0 as a register. When we want to set another register to 0, we might OR with AND with register 0, because register 0 is always all zeros. Register 1 is another temporary register that's used by the assembler, so that's off limits, we can't use it. We'll see several other registers are register 24 through 31 also have some special purposes, but we are also using some registers we've dedicated to the environment we've set up in the simulator. So I am asking you in the labs to limit register use to register 3 up to register 20. Okay, so any code that you're writing in the lab, make sure that you're only using registers in the range of register 3 to register 20. Okay, so let's go back and so number of storage registers, one aspect of our CPU or central processing unit. Another important component is our ALU, or our arithmetic and logic unit. Again, typically abbreviated to ALU. So our ALU is a device that does exactly what it sounds like. It performs arithmetic and logic operations. We are going to look at how we can construct a simple ALU in a few lectures from now, but for now just be aware that an ALU is going to be able to perform n-bit operations. So this is the number of bits that it can operate on. In specifically with the NIAS2, the operations are 32-bit. Okay. And there's typically a limited number of operations that it can perform. Okay, in the NIAS2, that is 64 operations. Okay, well, you'll see I continue to refer to the NIAS2 because this is what we're using in the lab. Of course, these examples will differ as you move to a different processor, but the underlying ideas and organization we talk about will apply to many different processors. Another key element inside our CPU is internal pathways or internal paths. And this is a electrical connection or a wired connection to allow us to move data around. These paths will be some number of bits in width, defining how many bits can be passed around at a time per transaction. And again, in the NIAS2, it's the internal pathways are 32 bits. Okay, so these internal pathways are pathways that exist specifically between our registers and our ALU, everything internal. I'll show you a diagram here in a minute after I present the next aspect of our CPU, that kind of a nice diagram, block diagram that summarizes up the various components. Okay, the fourth key component of our CPU is external paths. So this is the its means of connecting to the outside world, to additional memory, I/O. Okay, and these external paths in a will consist of a address path, a data path, and a control path. Okay, and we call this an address bus, a data bus, and a control bus. And this is what you would see in a typical 3-bus architecture. Some CPUs may have multiple data buses and multiple address buses, but we're going to focus primarily on the 3-bus architecture that has a single address bus, a single data bus, single control bus. Quite a common architecture, and this is the architecture used in our NIAS2. In the NIAS2, the data bus is 32 bits. Oops. And our address bus is also 32 bits. And we'll talk about what the meaning of the width of these buses are here shortly. Okay, 32 bits in our NIAS2. Okay, let's talk about the implications of the width of these buses right now. So the width of the data bus, as I said, with the internal path, that limits the number of data bits that can be passed back and forth in a single transaction between I/O and the CPU, or memory and the CPU. Okay, that number, the width of the data bus, this is what defines the bit width of your processor. So you may hear reference to the processor in your desktop computer being a 64-bit processor. What that means is the data bus is 64 bits in width. Microcontroller, said small scale processors that are used in microcontrollers, you may see processors defined as 8-bit or 16-bit or 32-bit. 32-bit was even common in desktop computers up till a few years ago. Okay, whereas the number of address bits that exist in a system, that defines the total number of locations that can be specified in memory. Okay, so in the case of the NIAS2, the NIAS2 can specify 2 to the 32 locations. 2 to the 32 locations amounts to a little over 4 billion locations. Okay. How are operations defined in our CPU, and what kind of operations do we need? Okay, so let's talk first about the operations we need in the CPU, and we'll think about this fairly generically, and you might be surprised that we can kind of categorize all operations into two main categories. The first category being a move operation. Okay, And those move operations might be internally between registers, or they may be to and from the arithmetic and logic unit, or they may be external moves to and from memory or devices, I/O devices. Okay, so that's one main category of operations required by the CPU. The second main category we can sum up as ALU operations. Okay, and as again the name of our ALU, our arithmetic and logic unit, suggests, examples of those type of operations include arithmetic type operations, add, subtract, negate, for example, or logical operations such as AND, OR, XOR, NOT, etc. Okay, so again, these being our arithmetic operations, and these being examples of logic operations. And these are just a few examples of, but many more exist. Okay, so those are the type of operations we need. So what information do we need to provide to the CPU in order for it to perform its operations? Okay, so what info must be provided to the CPU? Okay, well, clearly we must tell the CPU what we want to do. Okay, that information will be relayed or portrayed to the processor through some number of bits, so through some n number of bits. In the case of the NIOS 2 processor, you'll remember that I said that it had 64 operations, so we only need 6 bits to be able to define 64 different operations. So we have 6 bits dedicated to 64 operations in the NIOS 2 processor. Okay. What other information do we need to provide? Well, we need to provide the operands, or the source data that is going to be processed. So what are the operands? Okay, or so we may refer to this as the source. And often our source of data will consist of 2 sources, and I'll just list those as source 1 and source 2. Okay, what are we thinking about when we talk about sources? So my sources specifies things like the register, the memory location of a value, or sometimes a value directly. And you'll see what we mean as we talk about immediate type instructions, where one of the source operands is passed in directly through the instruction, the definition of the instruction, or the instruction itself. Okay. What other information? Well, we need to also know where does the result go. Oops. So we perform some operation on a couple of operands. We need to know where do we put the result. And this is often referred to as the destination. That destination will specify a register or memory. And we'll see here in the, maybe I'll extend this to say register, memory, or device. Okay. And even up here I said my operands specifies the register, memory location of a value. It might also well, we'll leave it at that, memory location of a value. We're going to see that devices often are defined through their memory location, but let's specify. We'll say it specifies maybe a device as well here as one of the operands. and what I mean by a device is maybe a input port and data from that input port. Just to remind us what the system looks like that we are referring to in our description of the aspects of the CPU and the computer itself. I think it's worth again referring to this kind of high-level block diagram where we see the CPU here in the block on the left. Okay, so this is our CPU, and we see what I talked about previously as these internal pathways, these external pathways, the ALU and the registers, and we'll talk about the control unit a bit later. And we also see these other external devices like memory and input and output ports that all are play into the information that we need to provide to the CPU as we tell it what it is that we want it to perform for operations, right? So we need to tell it what operation we want to perform. That may be an ALU operation. We need to tell it where the operands are coming from. They may be coming from a register, memory, may be coming from an input port, and we need to tell it where the result's going to go, and that again may be the register here again, maybe a memory location, maybe an output port. Okay, so that again, we'll keep referring to this diagram as we walk through the different aspects of the computer, and as we talk about providing the required information to have it perform the actions that we wish it to perform. Okay, let's look at what a binary instruction looks like. This binary instruction being our means of providing these details we talked about above to the CPU so that it knows what to do. So let's start by looking at a NIOS to I type instruction. I standing for immediate type instruction. Okay, so at the binary level, an I type instruction has a here's what each of the bits of that instruction is defining. Okay, so let's use an example, and for our example, let's use an add immediate instruction. Okay, so add immediate. So add immediate, or add I, as it sounds here, is an instruction that adds the immediate value being a value that's passed in, one of the operands being passed in through the instruction, through the code. Okay, you'll note that the this kind of syntax is used as we look at our instruction reference manual. You'll find that on D12. It uses a syntax that looks like this. To explain what's going on with the instruction. Okay, so let's look at what information is provided through this instruction, and as described here in this syntax that is describing what action the add immediate instruction performs. I'll show you an example from our instruction reference set here in a second. Okay, so first thing we'll see here is the plus sign that's added in here, which is defining the operation. Okay, here these two fields are defining where the operands are going to come from, or the sources. In this case, we see that one operand is coming from this immediate 16 value shown here in the 32-bit instruction word. Another one of the operands is coming from the register whose number is defined in these 5 bits shown as RA. Okay, and finally we see that the destination is defined in terms of a register as well, and that's register RB. So these 5 bits in the binary instruction are going to describe where the result should go. This little sigma sign here simply is indicating that the immediate 16 value is going to be sign extended. So just says that the sign bits will be extended to take up the entire 32-bit as required for the operation to perform correctly. Okay, let's look at the syntax for the instruction, the specific syntax for the instruction. This is the kind of pseudo instruction that's listed here, or the operation. Okay, so this is just describing the operation. Okay, but let's look at the assembler syntax. Okay, so the assembler syntax for an add immediate instruction requires that we put the add immediate instruction first. Next, we list the register that defines the destination, and next we define the register that contains one of the operands, and finally we pass in the immediate value that can be up to 16 bits through the instruction itself. Okay, so again, these 2 bits of information are the operand or the sources. Here's my destination register defined, and in this and then of course the operation that we want to perform. Okay, so we need to use our instruction set reference to make sure that we know the order of these operands and destination registers and what's expected by each instruction. To show a specific example of the use of the add immediate instruction, here's an add immediate instruction that's going to put the result in register 3 when it after it adds the value that's in register 4 to a value of 2. Okay, so that's the assembly language instruction for adding a value of 2 to register 4, putting the result in register 3. Okay, but if we looked up here at the beginning, what the processor is expecting, what the CPU is expecting, is this a 32-bit instruction word in this format that's shown at the beginning here. Okay, so how does that happen? Well, we write our instruction in assembly, and then a software package called an assembler takes the assembly language and generates the corresponding binary instruction word. Okay, so in this case, maybe I will grab this image here again, put it down at the bottom here. Okay, so in this case, an add immediate instruction, I'll show you where we can find this here in a second, but an add immediate instruction has an opcode that is 00. Well, actually, let me start with this. It has an opcode of 0x04. This immediate value is supposed to be a value of 2, and in register B here, you see that register B defines the destination register, so that should define register 3. Okay, so these bits should correspond to register 3, and the other operand is coming from register 4, which is defined in register A of our immediate type instruction. So here we need to, for this specific instruction to add 2 to the value in register 4 and put the result in register 3, our binary instruction word should be generated by the assembler that looks like this, kind of generically. But if we get specific to the bits, okay, let's look, actually let me do it like this, the specific bits that will exist in each of these locations of the 32-bit instruction word. Okay, are going to look like this. Maybe I'll write these in blue. Okay, so 0x04, so that's saying a value of 4 in hex. In binary, now remember I have 6 bits here, so in binary 04 represent with 6 bits is going to be 00100. Okay, a value of 2 represented by 16 bits is going to be 0000, 0000, 0000, 0010. Okay, a value of 3 to signify register 3 using 5 bits is going to be 0 and 0011. Okay, and of course a value of 4 to signify register 4 is going to be 0, 0, 1, 0, 0. Okay, so that is the specific 32 bits that the assembler will generate, which is the binary instruction word for this specific assembly language instruction that is instructing the CPU to add 2 to register 4 and put the result in register 3. Okay, so you might ask, where did we get this information? Well, if we have a look at the instruction set reference that I've been referring to, so we can find this on D2L under lab reference material, NIAS2 instruction set. This gives all the details that you'll need to know about any instruction for the NIAS2. So here's the same kind of information that I just presented about an I-type instruction. We see the layout of the bits in the binary instruction word. R-type instruction, we'll come back to that in a second, and J-type. And here is for, this is for an I-type instruction. Here are the details of what opcode is associated, right? Those 6 least significant bits in your instruction word are associated with each instruction that, at least in this case, each immediate type instruction. So if we look specifically at the add immediate instruction here, we'll see that add immediate has an opcode of 04 in hex. Okay, so if we go back and see here, here's where I specified the opcode for the add immediate instruction to be 04. Okay, yeah, so you can find any I-type instruction and R-type instruction in here as well. We'll look at R-type in a second, but of course you want to get into the specific details of the instruction. You can go to the details for every specific instruction just by, there's a table of contents at the beginning here, but here, for example, is the add immediate instruction. So we can see those same details. It shows the operation, right? It shows what values are the operands. Right, so we see what components are the operands here, right? RA and the immediate 16 bits are the operands. We see that RB is going to be the destination register. We see how to format the instruction in an assembly language, and then it shows an example. Okay, and then there's some more details below about specifics about the instruction. Okay. All right, let's so that's a I-type instruction. Let's have a look at an R-type instruction. Oops. So looking at a NIOS 2 R-type instruction, the R referring to register type as opposed to immediate type. Let's look at the structure of the 32-bit instruction word, binary instruction word for an R-type instruction. Okay, so this is, as I said before, is a binary instruction word, or what we may refer to as binary machine language. Okay, and again, we in this specific case, the instruction is such, the instruction word is laid out such that these two registers specify the operands. This specifies the destination for the result. In a R-type instruction, the operation itself is specified here. Okay, so with these 6 bits, we do have a 5 bits. We will see a few R-type instructions do use an immediate value. And the last 6 bits, which in the I-type instruction were used to specify the operation, here those for an R-type instruction, they're always 3A, which is basically telling the CPU that the instruction format is going to be R-type, okay, to distinguish it from an I-type instruction. Okay, as I said above, we would not write this instruction directly in the binary machine language format. This would come from an assembly language instruction, which is considered a higher level language, at least higher level than binary machine language. Okay, and we would get to this binary machine language, again, as I said above, through a software package called an assembler. Okay, an example, similar example to an R-type instruction, we'll use an add instruction. So let's use an add where, again, we said the register RC is specifying the destination, and registers A and B specify the source data. Okay, so here's my source, here's my destination, and here's my operation. Okay, and a specific example of an add instruction, an R-type add instruction, would be an instruction that adds register 7 to 8 and puts the result in register 6. Okay, if we wanted to look at a description of the operation, maybe I should have started with this. We probably should look up the description of operation. Description, oops, what I wanted to say here is description of operation. This is where, again, you should use your instruction set reference to make sure you understand how the instruction is being performed. And if you looked it up for this one, it would show this syntax that makes it clear that the register 7 and 8 are being added and the result being put in register 6. Okay, from this, maybe I'd like to, let's take this and move it down here. From this example of the R-type instruction, again, the processor needs this instruction in a binary machine language, as a 32, in the case of the NIAS processor, as a 32 bit instruction word. And we saw that for an R-type instruction, that instruction word would have this format. So after that instruction goes through the assembler, it should take on a format that coincides with this format shown here. Okay, so if I were to fill in the values here, we know that this instruction here, the operation is going to be an add operation. The destination register, we said we want to be register 6. The operands, or the input or the sources, are going to be R7 and R8. Here, this is simply specifying that this is an R-type instruction, so those bits are fixed for an R-type instruction, and we don't need an immediate value here for an add instruction, so these bits, these 5 bits, can just stay 0. Okay, so what does the specific bits look like? Well, let's fill them in. So working from right to left here, a value of 3A in hex, those 6 bits. Let me just divide the bits up into their subsections. The 6 bits associated with a value of 3A, 3. Oops, let me go back to blue here. 3A. So again, only have 6 bits here, so that's a value of 3A. Again, I didn't need the immediate 5 bits, so those can remain 0. An add instruction, so we could again go to our instruction reference set. Let's go back to that now. There's the specific add instruction. Let's come back to that and let's just look at all our type instructions. I went by them here, I think. No, I did not. And those are R type or I type instructions. Here's our R type instructions. So we're looking for the add instruction. So looking at the add instruction, if we find it here, we see the add instruction is right here, and that has a opcode or OPX code of 31 in hex. Note that it's in hex. That's what the 0x means in front of that. Okay, so if we go back here, we know that the add instruction will have a value of, I'll just write it down below, of 0x31 in hex. 31 in hex is 110001, represented with 6-bit binary. Okay, and then we can go and fill in the rest. R6, so register 6 is with 5 binary bits is 00110. R8 with 5, represented with 5 bits, is 01000. R7 is 00111. Okay, again, let's just jump back to our instruction set reference here again. So this is the all R-type instructions listed in a single table and the OPX code associated with them. If we scroll down to the specific instruction we're interested in, here's the add instruction, and we can see those details that we were that we outlined in the written example. Right there we see the operation. Okay, so we see the operation, whatever values in register A and register B is going to be added and placed in register C. Here's a example of the required syntax where we've specified which register in those 32-bit instructions are associated with operands, which is associated with the destination. And here's a specific example, the same as the example that I used. Okay, and some more details down below about that instruction. Okay, let's just finish up with one final instruction type, and that is a J-type instruction. So this is the only other instruction type that exists in our NIOS 2. So just pulling an example from the textbook, the J-type instruction is specifically used for a call instruction. A call instruction, we'll see later on, is used to branch our code off to a subroutine. And that's where the J-type or like jump type, the J from the J-type instruction comes from. It refers to a jump. The details of how the binary instruction word are created is a little bit interesting. You see in this example here below, using a call. So what we provide here is where specifically we want to redirect the code to, or where we want to jump to, by saying call, and we put the address. And we'll see later on that we often use address labels to make this more readable. Okay, and that instruction or that address is actually taken by the assembler process, and it actually takes the address that's provided, divides it by 4 when it stores it in the instruction word, and only actually requires 26 bits to specify a 28-bit address. And why is this? Well, we will discover that all of our instructions in the NIAS2 are 32-bit in length, but the processor is able to address data byte by byte. So, and since instructions will only ever be a new instruction will only occur at every 4th location, we don't need to specify the final 2 bits of the destination address. Our instructions are always going to be word aligned, we'll call them, and they'll never be offset by anything other than a multiple of 4. Okay, so that allows us to store a destination address that truncates those last 2 bits off and gives us a little bit more flexibility in the number of locations that we can specify with a call instruction.